Hello everyone and welcome to another episode of Investigation. In today's episode of Investigation, I will go over the LHpitals Rule. But before that, we will get started with a simple daily problem. And this is also the last episode of the all derivative rules, which means that you have mastered all derivatives if you've watched all my tutorials, and you can differentiate almost all of the functions that you will encounter in calculus. Let's get started by the first question. The first question is find the second derivative of this function, and we want to find that. Obviously, we want to find the first derivative first, so the function itself looks like this. We want to find the first derivative. So if the first derivative of this, we need to use the chain rule over here. We would get, this is the cosine of the log of x, and the derivative times the derivative of log x. And take a note over here that log x without any base indications over here, we assume it to be log base of 10. And this, we can use the log a of x, so that will be 1 over the ln of a times x. We can write that as a quotient because we need to differentiate again, and the easiest way of doing that is to use the quotient rule over here. So write it as a quotient like this, and we want to differentiate this thing again. So what we have is the second derivative of this, the same expression. So it's basically the derivative of this, and we can use the quotient rule. So let's denote f of x as the cosine of log of x, and the g of x would be the ln of a times x. This. And the derivative of f with respect of x is equal to this, so that's negative sine log of x. And when you multiply this, let's give us a little bit of free space. We need to multiply this by this derivative of log of x, so that is still ln of a times x. And we have the derivative of g with respect of x. Notice that we are not using the product rule over here. This over here is a constant. So this is a constant. Let's write this. This is a constant. And we can just use the constant multiple rule. That is actually, in fact, equal to ln of a. Just straight up ln of a. And let's try to differentiate this thing now. Give us a little bit free space. So this is equal to, we have, went outside of this page, but it's okay. This over here, we can do this cross multiply. This times this. Notice that this part cancel out. So this part and this part cancel out. So what we actually have is this negative sine of log of x, that we need to subtract this multiplied together, and that is actually equal to, we need to subtract cosine of log of x, like this, times ln of 10. So something like this. And we need to move this a little bit over. Oops, that is not what I want. Oops. Okay, there we go. And ln of 10 and over, we need the original g of x, which is the denominator. Let's learn 10 of x. We need to square that. Be sure to square both terms. And this is our answer to this problem. Obviously, you can split it up into two terms, and you can cancel out one of the ln of 10 with this, but there's not a whole bunch of purposes for that. And according to that, it's not really simplified a lot, so we will just keep it this way. Let's look at the second one of this. We want to find the 100th derivative. That is a lot, and you don't want to bash that. That is very hard to bash. You need to find some clever way. Looking at this, x plus 1 to the 99th power, we notice that this is a polynomial because it's just, we can express it as a binomial theorem. So something like this, plus dot 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 plus 1. This thing is a polynomial, and we know that when we are differentiating polynomials, each time when we differentiate, we are actually going to get one less degree. So for example, if we differentiate this thing, we will get 99x 98 plus 99 times 98 x 97 plus dot dot dot, and then the 1 just is gone. And this thing has a degree of 98. So the zeroth derivative, so the original function, so f, is this, f of x. F prime of x, so let's just write it as f parenthesis of 1 of x. That's degree of 98. And if we have dot dot dot, we have let's say f parentheses of let's say 99 of x, we just simply have that is just equal to some constant, because if we differentiate 98 times, this 98 will eventually become 0. And it is very easy to deal with when we are dealing with a constant, because we need to take one more derivative of that. So that would give us, so that is just equal to 0. Don't overcomplicate this thing, because this is really easy problem that we're dealing with. Now let's take a look at LHpitals Rule. In LHpitals Rule, it states that if the limit of, so we have a requirement, if the limit of as approaches something of f of x is equal to 0, and the limit, so we have the limit as f(x) approaches c of g of x is also 0, then we have the limit as x approaches c of f prime of x over g prime of x is equal to L, and this L is equal to the limit as x approaches c of f of x over g of x. So if you cannot differentiate, or when you differentiate it, it is in a indeterminate form, then we can take the derivative on both the numerator and the denominator and evaluate that value. And or you basically have the same theorem, same rule, but instead we can apply it when this number, both of these numbers, has to be plus or minus infinity. That also works. But do not get these two separate rules, basically separate rules, but they're under one name, mixed up, because it does not work when there's like 0 over infinity, because that is actually a definite form that's just equal to 0, right? So we will prove a special case of LHpitals rule. That is the first section of the theorem. So the first section of the theorem, we'll try to prove that. And if we start with f prime of a over g prime of a, we want to prove that this is equal to the f of a over g of a. And we can try to prove that using the definition of derivative. So, when we're trying to prove that, this numerator is actually equal to the limit as x approaches a of f of x minus f of a. Notice here we are actually using a, not h over here, but it's basically the same rule that we're using here. And this is over x approaches a also of g of x minus g of a of x minus a. And we can have that. But then they have the same denominator, so we can just get rid of the denominator and combine the two limits into one because they're approaching the same thing over here. Both of them are approaching a. So that's the limit as x approaches a of f of x minus f of a over g of x minus g of a. Want to evaluate this thing. How do we do that? Well, we've assumed that both of f of a and g of a are 0. Because when we're applying LHpitals rule, we first assume that this is true. Over here, we said that we are proving this first case. So, both this and this are equal to 0. What we have over here is just the limit as x approaches a of f of x over g of x. However, there's no a involved in this thing. So over here, you might see what we are going with. This thing doesn't exist really because there's no a involved in the expression here. So what we have here is just equal to f of x over g of x. So this expression remains true. Thank you for watching this episode of Investigation, and thank you for watching the whole series, and I've done it. I will still get back to competition math really soon, so stay tuned for that, and goodbye.